Oh, sorry, Archie. Hey, didn't see you there. My bad. So today is periodic table time. Follow me. Since we're talking about periodic tables,
Are you talking about these periods?
no, silly goosey. We're talking about the arrangement of elements that go by increasing atomic number. But now, how about you join me and we go back in time when scientists were spitballing ideas and coming up with ways to create this. Way back in the 1790s, when painters with real cameras of today
Antoine Lavoisier
composed a list of known elements like oxygen, carbon, gold, and silver. We can say that he was the one who sparked the fire so that we could discover more elements. As we move forward to the 1980s, we have people like Henry Moseley and Newlands who start organizing the elements by atomic mass and number. The arrangements of the elements in the periodic table is called the periodic law. Believe it or not, today, the periodic law is actually the increase in atomic number. And
Can I go to class now?
dude, I'm in the middle of something. Can't you just let me finish? God, so inconsiderate. Now this just doesn't stop here. Mendeleev actually saw a connection between the numbers and elemental properties, such as color, density, metals, nonmetals, and metalloids. Since there were many comparisons between elements, scientists started creating families and groups for people to easily identify them. Now, I'm going to pass you on to my main man, Nick. Here we go.
Thanks, Nick. Now than just one or two groups, these are a lot like high school social groups. They have some differences, but some similarities. First, let's start with the metals.
Metals are malleable, ductile, conduct electricity, and have a metallic luster. They are what make up most of the space in the periodic table. They even have families like alkali metals, alkali earth metals, lanthanides, lanthanides, and transition metals. Then we have nonmetals. They are poor conductors, not malleable or ductile, have no metallic luster, and high electronegativities. Their families are located on the right side of the periodic table. We have halogens, noble gases, and just nonmetals. Next, we have metalloids. They have characteristics of metals and nonmetals, and they are also semiconductors. They include boron, silicon, germanium, arsenic, antimony, and tellurium, but not aluminum. They're a little staircase you see on the right.
Yash, wake up!
Valence electrons!
Gosh, Yash, stay awake. Yeah, valence electrons. They're the outermost electrons on the atom. The most desired amount is 8, which our friend the noble gases have. Not noble enough to share them, though. Just kidding, they can. Valence electrons don't just stay there and look pretty. They also control how the atoms attach to each other and if they attach. As you can see here, each group has a certain amount of valence electrons, but they do have some exceptions to it. Hydrogen, helium, lithium, and beryllium only have 2 valence electrons. These are like rule breakers of the group.
Hi.
Valence electrons are not the only numbers you see though. If you notice on the sheet, there are 3 different types of trends you may notice outside the periodic table. They are ionization energy, electronegativity, and atomic radius. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. Ionization energy increases as you move from right and move up. Another is electronegativity. Electronegativity is the measure of tendency of an atom to attract a bonding pair of electrons. And electronegativity increases as the same as ionization energy as you move to the right and as you move up the periodic table. The last trend we're going to talk about today is called the atomic radius. The atomic radius of a chemical element is a measure of the size, and it increases as you go down the periodic table and increases as you go left of the periodic table.
Thank you.